Filip Rozpedek. I'm a PhD student in the group of Stefanie Wehner at QTech in the Netherlands. I work in the quantum internet roadmap, and my talk will be about realistic parameter regimes for a single sequential quantum repeater. And our work is available on archive under this number. So we start with short motivation. Transmission of quantum information over large distances is a fundamental challenge. And in particular, if we want to communicate over channels such as optical fiber, then the transmissivity or the probability of successfully transmitting the photon over this distance will decay exponentially with distance, where L0 is the attenuation length of the channel. And then what has been also shown is that if we want to perform quantum key distribution over that channel, then the secret key rate defined with respect to the number of users of that channel will necessarily also decay exponentially with distance. And so the idea here is that quantum repeaters were introduced in order to overcome this limitation. And that brings us to this fundamental question, when does such a quantum repeater really repeat? And so to answer this question, we consider the following setup, where firstly Alice and Bob are given access to a direct transmission channel of transmissivity eta, which is a pure loss channel, so with probability eta, the photon makes it through. With probability 1 minus eta, it gets lost. And then we look at, we optimize over all possible protocols that Alice and Bob can implement to generate secret key over that channel. And such optimal key rate, the capacity of this channel for the pure loss channel is known and is given as a following function of this transmissivity. And then as a second step, we give Alice and Bob an access to a quantum repeater, which is just some device that is placed somewhere between Alice and Bob, possibly in the middle. And this device is going to be imperfect, so it's going to have some intrinsic losses, the operations that it will perform will be imperfect. And so we model all these processes. And then for some specific protocol that we implement using this device, we then calculate the expected secret key rate. And what we want to achieve is for this secret key rate to be larger than this capacity of the direct transmission channel, because if this is so, then we are guaranteed that we are doing something that we are achieving a rate that it would not be possible to achieve if we did not have access to this repeater. And so such a proposal for a proof of principle repeater has been proposed in this paper. And so this setup is motivated by experimental simplicity. So the quantum repeater consists of two quantum memories. Both of them have interface to photons. And here we will focus on the sequential version of the protocol considered here, which means that while both of those memories have interface to photons, only one of them can be used at any given time. And that's motivated by the fact that many physical systems, such as NV centers or trapped ions, will have access to such a sequential interface. And so in this protocol, firstly, the quantum repeater generates entanglement between this quantum memory one and the photon. The photon gets sent to Alice, and then Alice informs the repeater whether she successfully received this photon or not. And this gets repeated until success, in which case Alice performs a BB84 measurement on the photon. And then the same is attempted on Bob's side, but while the photons are being sent to Bob, the state stored in quantum memory one will inevitably decohere. Then after Bob has also succeeded, the repeater performs a Bell measurement on the two memories, communicates the classical outcome to Bob, and so that Bob can correct, and in this way Alice and Bob obtain one raw bit, and from those raw bits they can later distill secret key through classical post-processing. So in the ideal scenario, if this repeater was perfect, because both of those two links are independent, the secret key rate should scale with the square root of eta, while the capacity was shown before in this high loss regime scales linearly with eta, and so such a repeater should then be able, in this ideal scenario, to easily overcome the capacity. So what is new in our analysis? So firstly, we improved the rate by also performing a 6-state version of this protocol. And in particular, we supplement the standard one-way error correction scheme with advantage distillation, which is a specific two-way post-processing scheme, two-way error correction scheme. And in particular, we use the advantage distillation scheme proposed in this paper. Secondly, we introduce a new set of benchmarks that will guide the way towards the quantum repeater. And thirdly, we introduce a new parameter that we call a cutoff, which, by optimizing over which, we can significantly improve the rate. And so I will now briefly describe how this cutoff works. But before, I just wanted to mention that we have analytical tight bounds for the number of channel uses needed to generate one raw bit between Alice and Bob as a function of this cutoff. So as I mentioned, there's this problem of this decoherence of quantum memory 1. So what happens is that if Bob needs huge number of attempts in order to receive this photon, then, for example, if he receives the photon after 700 trials, then the state in quantum memory 1 might have decohered so much that no key would be extractable from the effective resulting state. So what I mean here with this cutoff is that we just impose the cutoff on the number of attempts that Bob can perform. So let's say if after 300 trials Bob still has not received the photon, then both memories get reinitialized and the whole procedure gets repeated with, again, sending photons to Alice. So of course we need to keep track of the number of channel uses that were required on both sides, even for the rounds that finished with failure. But now we are guaranteed that if Bob also succeeds, the resulting quantum state has much higher quality. And so we have this trade-off between, as a function of this cutoff, between the quality of the resulting state and the number of channel uses that is required. So how does this cutoff help? Well, that we can see on this picture. So here we have applied our analysis to the NV center setup with cavities. We considered this plot is for a fixed distance of 15 in the units of attenuation length of the channel. And in particular, here we choose the channel of this attenuation length. And the motivation for that is experimental, because this was the channel that has been experimentally realized in connection with NV center setup in the loophole-free bell test in Delft. And so we here plot this for a different set of parameters. So we have these expected parameters, and then we see what happens if we reduce a little bit the intrinsic losses, or we reduce the operational errors of our devices, or we reduce the decoherent rate of our memories. And so the first thing that we see is that for this distance, the cutoff is essential in order to be able to generate secret key, because if we impose no cutoff, so we move towards infinity on the horizontal axis, then the rate is 0 for that distance. And secondly, what we also see is that the optimal cutoff that maximizes the rate is highly dependent on the parameter. So it's vital to be able to independently optimize over this cutoff for every set of parameters. Then we could also ask the question, where exactly should we place the repeater? So in the article that introduced originally the scheme, it was also suggested that the problem of decoherence can be overcome by shifting the repeater towards Bob. So if we shift the repeater towards Bob, we can make sure that the average number of attempts on Bob's side to receive the photon could be made smaller than the coherence time of this quantum memory QM1. And that's what we see here. So here we fix the total distance between Alice and Bob to 11. And so the beginning of the x-axis is for the middle positioning. And so what we see that for this distance, if we don't apply the cutoff, we are not able to generate any secret key if repeater is placed in the middle. But then if we shift it towards Bob, then at some point it becomes possible to generate secret key. Well, if we apply the cutoff, then the optimal positioning of the repeater is in the middle, if we optimize over this cutoff. So having introduced those two methods, we can now compare them. So here, for the green lines without the cutoff, for every distance, we independently optimize over the positioning of the repeater, while for the scenario with the cutoff, the repeater is always placed in the middle, but for each distance, we optimize over the value of this cutoff. And so what we see that after a certain distance, the secret key rate drops to 0. That's due to the noise caused by the dark counts. But we see that the cutoff is much more robust against the dark counts than the repositioning method. And that is because if we shift the repeater towards Bob, we of course make the link Alice repeater much longer. and as a result, we decrease the signal to noise ratio of that link. And so because this link is now so long, for much shorter total distance, we reach this threshold where we are no longer able to generate key. So now I will go over those new benchmarks that we introduced. So the motivation for that is, as I mentioned at the beginning, ideally our comparison reference direct transmission scenario would be a pure loss channel where the optical fiber would be our comparison channel. But since in any realistic implementation of the direct transmission, where Alice will have some imperfect devices, some imperfect sources, Bob will have some imperfect detectors, so it's not so clear what will be this reference direct transmission channel. And so to make it a little bit more systematic, we can say that in the corresponding direct transmission scenario, there is some photon source that with certain probability PEM emits photons that get successfully coupled into the fiber. Then we might need to do some post-selection because only photons within a certain time window or of certain frequency are useful to us. Then we will have our actual channel of the optical fiber. And finally, we will have detectors that are also imperfect and might have dark currents. So in this most stringent scenario, our channel is just the optical fiber. And so all those other intrinsic losses are in the labs of Alice and Bob, and so they will not be part of this channel to which we compare ourselves for direct transmission. But then if we are less stringent, we could say since any realistic implementation of direct transmission will also have those intrinsic losses, in this other scenario, we will basically include all of them in our reference channel. So that will constitute a different benchmark. Then we could also ask the question, what is going to be our direct transmission channel? So before, I mentioned that we will consider it as a pure loss channel. But because we also have this finite probability of emission, we should maybe consider the scenario where we consider the pure loss channel, but with the restriction on the average number of photons that we can input into this channel per a single channel use. And then if we also include detectors into the channel, well, then our channel is no longer a pure loss channel. It will be a thermal channel because detectors have dark currents that are caused by thermal photons. And so in that case, we consider a thermal channel with the mean number of thermal photons that corresponds to the dark out rate of the detectors. So now we can perform the comparison of our expected rate with all those benchmarks. So we have 3 cases corresponding to which of those lossy processes are included in the channel. For cases 1 and 2, we have the pure loss channel benchmark and the pure loss channel with the restricted number of photons that we can input per channel use. And then in the scenario when we included detectors in the channel, we have the thermal benchmark. And finally, we also have a benchmark that we call direct transmission with the same devices and the same protocol. So this corresponds to the scenario where we effectively implement the same protocol over the direct transmission channel. And so we see that the last 2 benchmarks can be easily overcome, while the other 4 are within the experimental reach with such a setup. And if we improve the parameters a little bit, then we see that we could achieve a rate that over a certain distance overcomes all the benchmarks. And so in such a scenario, in this regime, we would have a repeater for repeating key in the most stringent sets. And so to conclude, we have a universal model that is applicable to a wide range of physical systems, such as NV centers or trapped ions. And our mathematical notebook is freely available upon request for everyone to plug in the parameters of their setup and to compare the rates with the benchmarks also defined for their setup. Thank you.